I'd like to introduce Eric Xing. Eric is a professor in Carnegie Mellon University. He has done lots of work spanning many areas of machine learning, including developing statistical machine learning methods and algorithms, and also lots of applications in social networks and computational biology, and even computer vision and natural language processing. He recently is also pushing this direction of combining machine learning with a large-scale system and architecture, and he's going to tell us more about his venture in this direction.
All right. Well, it's such a great pleasure to be back in Berkeley, especially I saw my old advisor, Professor Karp, in the seat. It's really a great honor to have him here. And I saw Mike and Stuart yesterday, so it's a very good reunion, after so many years. Yeah, I'm going to talk about some of my recent work in the so-called system and algorithmic design. I heard a few talks this morning already. This one will be a little bit different in terms of the flavor and the style. Okay, I'm going to also present a few theorems, but without proof. I'm going to more focusing on presenting the open problems that we are facing, in designing efficient, deployable machine learning algorithms. So this is perhaps a way, Okay, this is the way many people see machine learning. Maybe you guys will be laughing at it, but people do see machine learning like this. They want the machine learning algorithm to be a black box that you throw in data and that you get the answer out of it, which is kind of naive. But if we look at ourselves and how we see computer, it's no different from here, right? We are programming, on a black box, writing algorithms, and we wish the box to do what it's supposed to do without any error, and then we can analyze our algorithm in terms of its convergence, bounds, and all that, with no worry about whether the machine goes wrong or right. That's why in many of the theorems, you don't see any coefficients talking about the machine behavior. And that's actually not necessarily the ideal situation you are going to face in industry. So here I've been working in industry for a while, and I had a startup. And our goal is to offer machine learning solutions to big data users. And typically, after you have the data and you are assigned the task, and given the hardware, you need to figure out this whole thing in the middle, which includes algorithm, model, implementation, system architecture, and so forth. And the kind of solutions that we are having now is really a handcrafted, monolithic kind of one-off solution, one for each particular problem. Maybe the same problem solved by different people will be also different, therefore many of the results are non-repeatable. So it's actually a big barrier right now, causing machine learning and AI not to be very popular in the greater industry. And this is actually one of the personal kind of experience I had before. We, many years ago, developed a pretty good algorithm for social network embedding, which were able to, in fact, embed a 1 million node network using a single machine in like a few minutes. So it's pretty amazing. We published quite a few papers on this topic. But then, we want to bring this algorithm to Facebook. And the kind of problems they give is this big. They say, 1 million is pretty good, but after all, my network is a billion. Maybe you should demonstrate your algorithm on 1/10 of that, which is 100 million. Okay, and of course they are going to offer you not one machine, but maybe a cluster of 1,000 machines. Well, if you are naive and say, well, let's use Hadoop and deploy this algorithm on 1,000 machine, maybe I should see a 0.6 minute kind of completion because my resource grow 1,000 times, my problem grow 100 times, right? But the truth is that if you really run it, as we did, it doesn't finish in more than a week. So why that's the case? That means the system is not ideal. There are something going on in the system which is beyond what the algorithm can handle. So that's why I want to take another look of this problem which we often solve in machine learning and see how really to ground these type of solutions on a real computational infrastructure, right? So here is a typical machine learning setup. You are doing a optimization problem where you set up the loss function, which is your model. You specify your parameters. You may also introduce some regularizers to control the complexity, or maybe introduce prior knowledges. This is the part of maybe 95% of machine learning. The other 5% maybe goes to the algorithm. We come up with, very typically not a closed form algorithm, but a iterative convergent algorithm, finding a fixed point and iterate using some update equation. So this one is the holy grail of that algorithm. You need to figure out whether this one is a gradient, a projected gradient, or a smooth version of that, or other, second order terms and so forth. And then you're going to do this iteration, hopefully without any trouble. But in modern days, this particular operation is going to be under severe challenge. Why? Because in many industry problems, we are really facing either very big data or big model, which lets you to face this scenario. Maybe you are going to, every time, update a gigantic vector or matrix of parameters, which could be having 100 million parameters, which is not unusual in deep learning, for example, these days, or even a high-dimensional regression problem. Or if you really are working on huge data, then this one also will explode, and therefore you are going to swipe, a terabyte of data maybe in every iteration. That's also very, very difficult. And consider doing this, for indefinite number of iterations is something quite challenging, because in that case, you probably need to think about solving the problem not on one machine, but on many machines in the distributed environment. And then how to let all these machines behave as if they are a single machine is actually a pretty serious and difficult technical problem. It's not only an engineering problem. A programmer assigned to this job usually cannot figure out how to do it if they don't know enough machine learning, especially how to do it right. And people tried solving these problems using Hadoop, for example, or using Spark, very often not having a lot of success. And I'm going to say a few words about why that's the case. Okay. So here is maybe a more detailed look into that. So how do we parallelize a program if you have multiple machines? Well, basically this particular step, which is the consequence of maybe a long effort of a machine learning theoretical study, will eventually lead to some kind of update procedure that you need to now kind of bring them into a parallel version. And for mathematicians, I think the greatest kind of need we need to address is to make these two things equivalent so that they mathematically give you the same answer. And then one of the things we come up with is to make them synchronizable, so that when each machine are doing their job, have done their job, they should shake hands and exchange their nodes so that we make sure everything go okay, then go to the next iteration. Well, this is actually in practice a very expensive step, even though in our analysis of the algorithm we don't see that. We usually assume that the synchronization takes zero cost, and also the synchronization should not have any faulty operation. And also the message can actually be transmitted across the internet or the Ethernet so that you don't run into network congestion and so forth. None of these are true actually in a big distributed system. Therefore, for a real distributed environment, you either do this kind of synchronization like what Hadoop will automatically offer to do for you, and you pay a huge cost in basically latency and in communication and overhead. Or if you just remove the synchronization, you are likely to break this equivalence and run into a divergent algorithm. That's typically happened in many of the implementations. And that brings us to basically maybe a renewed effort in asking how to analyze efficiency in a practical algorithm that is really deployed in the field and doing this combat. Right. So if you look at this typical bound that we often see in our algorithmic analysis, which gives you a rate of convergence in the order of iterations. And first of all, this particular analysis doesn't tell you how much iteration will cost. And also, there isn't a coefficient telling you the status of the machine and other systems. But in reality, there are a lot of subtleties. I just want to point to maybe even one. You'll probably see many papers, especially nowadays, this deep learning papers, which almost force you to use a multi-core or multi-machine environment because it's so big. Then, very, very interestingly, the reported improved performance on a cluster or on a multi-core system is typically in the form of a throughput. Throughput means that the amount of data you can process per unit amount of time. And as a result, if you have more machines, your throughput will grow linearly. Very, very happy results. What is not often shown in a real experiment is this curve, which is the number of iterations it takes to converge. Okay, Because if you do a lousy job, in synchronization, when you add more and more machines, mathematically the quality of each iteration is degrading because they are going to be less and less synchronized. They're going to introduce more and more error. Therefore, the effectiveness, the mathematical progress or statistical game of every iteration could be very worse. Therefore, this is an experiment we did actually with some cluster setup. You can see that as you had more and more machine, the number of iterations it takes to converge to the optimum spot is going to be bigger. But ideally, what you want is this. When you change your machines, you are going to experience the same number of iterations, and then you have a bigger throughput, and then when you multiply this together, you get a faster convergence in the wall clock sense, not in terms of the number of iterations, right? So how to achieve that point? Well, this is a slide I'm going to skip. I meant to say that to achieve this, it is not enough just to design a smarter algorithm or re-engineer the system. Because very often, our machine learning algorithms has very interesting mathematical behaviors which may offer different opportunities than other standard computations, such as a database operation, query optimization, and so forth. And also, by knowing the details in some of the systems, sometimes the algorithm can be redesigned or optimized so that you can leverage on bidirectionally the opportunities out there. And this is in contrast with many of the traditional system work or algorithmic work, which is really transaction-centric. You want to maintain the algorithm to be transactionally rigorous, and therefore the automatic correctness of the algorithm is the key of the operation. In machine learning, after all, we are solving an optimization problem. Right? Mathematically, your goal is to go to the top of this hill. Whether you go this route, that route, you make a mistake in the middle, may be less relevant if you still know the whole direction. Right? So that's why I think there is an opportunity there to restudy system design. One of the way people do this exercise is like this: to create a super, specialized and complicated thing which can work on one problem, but if you ask this guy to do another job, say hunting in the forest, maybe this guy will run into trouble, right? So what is really needed is to, ask whether such a system and algorithmic co-design can lead to even a generic solution which support not only one algorithm, but many, many different problems and many algorithms. So I'm going to share with you some of the work took place in my group and also with my colleagues at CMU in these 4 dimensions on how to develop a general purpose architecture for via system and the algorithm co-design to solve this particular step more effectively on the distributed environment. So I'm going to begin with something very simple. So the first thing people ask when you have a distributed system is to decide on what to distribute, right? So for example, here I have a scenario where the data can be very big. I have another scenario where the parameter may be very big, or maybe both are big. Then in fact, the problem even started from here. When you divide the data to different machines, and when you divide the model to different machines, the type of statistical loss or the type of care you need to bring in to make sure things are not going wrong is going to be different. So let's take a look at how to divide this. Say many of the distributed implementations of a large-scale algorithm, the first thing come in mind is to do load balancing, right? Load balancing in this particular case means the following. Say I do a very large regression problem, and say this particular regressional vector is 1 billion dimensional. Well, don't ask me where I get this problem. In fact, this problem is solved in Google almost every second. So it is actually a very real problem, even though mathematically we can ask, well, regressing on a 1 billion dimensional kind of problem seems to need infinite data and so forth. But that's actually a different discussion we can have, because most of these problems will have regularizations. Therefore, there are still in practical value in having a convergent solution. But engineering-wise, how to solve this using a computer cluster is actually quite interesting. You can imagine that maybe we need to do the following. We need to divide this big vector into chunks so that they can be put onto different machines, right? But that actually is not trivial, because we knew that between different dimensions, you can probably show that there is a chance that the parameters can be coupled. They may be even collinear if you measure the same feature twice using different devices. And if that's introduced, then if your synchronization is not working right or not synchronized at all, and they are still computing in parallel, then you are going to run into the statistical inconsistency problem, and then the problem can be divergent. And this is actually the first hurdle already to overcome, when you want to develop a so-called model distributed problem, implementation. And there has been a number of work already there. And the first idea to come is to maybe have a random partition, betting on the chance that the problem is sparse and the coupling between dimensions may be weak. You can prove that the amount of efficiency you can get out of it is going to be a function of the diameters of the data, basically how strong they are coupled together. But this is a pretty weak guarantee because in practice, you're almost always likely to run into strongly coupling problems, especially in high-dimensional settings. So that gives us the opportunity for maybe a system co-design. Maybe we should think about a system which can dynamically schedule the task in a structured aware fashion by examining basically the dependencies among dimensions in a regression problem or in other high-dimensional problems. Well, that creates, again, yet another problem, which may be even harder, because testing the dimension or the correlations between dimensions in a very high-dimensional problem by itself is a very big problem. It may be harder than even the regression problem itself, right? So how do you, heuristically or systematically solve that? Well, in there, you have to leverage on some other properties in machine learning. For example, in machine learning, especially in high-dimensional regression, empirically people observe that even though you have a very high-dimensional problem, not all dimensions are equally important. If you do the iterative convergent operation, maybe every time a very small fraction of the coefficients are actually changing, and many other things are not changing, right? And this actually creates you an opportunity. Maybe we should focus on the scheduling on those very, very small amount of changing dimensions where you are likely to feel an impact. And then if you can divide those dimensions into different clusters cleverly, maybe you are going to have a speed up. So in that, there has been a number of heuristic or formal ideas to do priority scheduling and block scheduling. The idea is to really break apart highly coupled, bring together highly coupled dimensions to the same machine and detect independent dimensions to different machines and then allow them to run in parallel. And this algorithm or this approach is called the structure-aware parallelization (SAP). And the system part is to basically make this procedure automatic so that the people hopefully in the future don't have to do it by themselves. So we actually developed a program interface which allows people to specify the dependencies and schedule them without touching the system details. When these are done, the results are actually quite interesting, right? You can see that by comparing an unscheduled one and a scheduled one, you can see a dramatic change of the convergence rate in the experimental setting and also across different models. And you can even prove, in fact, that this type of speed up is enjoying a convergence guarantee, but also with a rate now proportional to the number of machines that you are going to bring in. Of course, this particular step here and here requires you to divide the data nicely. Here there is a little term that tells you the cumulative spectrum diameter of the subset of data on each machine. If you can reduce them effectively, then this term will disappear. Then you get the p-fold upgrade of the speed. Then the second problem that we are facing is that now that you divide your job, and hopefully they give you a nice theoretical insight, even guarantee on the correctness, but you still need to communicate, even though not so often. So how do you communicate? Typically, we don't ask this question. We think, like Hadoop or like a single machine, communication shouldn't be seen by us. Somehow it's automatically taken care of. Let's say, for example, in this particular, now data parallel problem, which makes the problem setup a little bit simpler, I'm going to run maybe a proximal gradient algorithm. And from the key updating step in here, here, and here, one can easily identify maybe which one to be the aggregate form happening on maybe a centralized form. And maybe some other forms are in the decentralized way. For example, the data-dependent computation of the gradient could happen on each server machine or on each client machine because they can be obtained from a subset of data. The aggregation of all these different sub-dataset dependent gradients can be happening on the center, the master, for example, by a summation, and then the projection to a particular constraint space could also happen on the server. So these are, maybe a top-down hierarchical design. But then when you are putting this into a system, how basically, this particular step is going to be dependent on the effectiveness of the communication. Shall I wait for every machine to give you this, or shall I allow some asynchrony, right? In the past, people have been heavily relying on this model, which was actually a very famous one proposed by Valiant and McCon about 20 years ago, called the bulk synchronous parallel model, BSP model, which means that you are going to set up barriers after each iteration, and when communication happens, no computing should happen, and when computing happens, no communication should happen. And this actually can be proven leading to consistent and serializable results in parallel setting. And there has been a lot of papers on that. Hadoop, Spark, for example, are all built on this so-called bridging model between communication and computing. But as I said, bridging is very difficult and expensive, especially when you want to do it iteratively for a few thousand times in the machine learning algorithm. So how to avoid that? A couple of years ago, Chris Ray proposed an algorithm called Hogworld, which basically says that maybe the folklore is right. You just ignore the communication. You have multi-core machines. You just divide your job into different machines, and then let them all do their job, and then come back to you asynchronously, and you just update or aggregate on whatever you have at a particular time point, right? And there are even theories behind that to suggest that this is the right thing to do, because most of the high-dimensional problems are sparse. If you have this subset of data and that subset of data, they may not touch in the same dimension on different cores. Therefore, you are not likely to have a collision, right? But it turns out that this algorithm isn't working very well in the distributed environment. By the way, they work well on parallel environment. There is a subtlety between parallelism and distribution. Right? Parallelism usually corresponds to multiple cores on a single machine. The communication latency between different cores are quite small, even though they are not zero. But across different machines in a cluster, the latency could be seconds or even longer. And that actually, in the end, affects the results. In fact, you can see we have a theorem showing that the quality of the solution depends on the mean and the variance of the latency between different machines. So as a result, maybe the straightforward idea is to redesign the system a bit, okay, to hopefully put a bound on the latency you can experience. Rather than going the extreme of a total synchrony or going to the other extreme of a total asynchrony, you want to stay in the middle and bound the amount of asynchrony that each machine can allow, so that you communicate only when this bound is exceeded. Okay, this is called the still synchronous parallel algorithm bridging model. And again, the system people are obliged to provide you a nice program interface so that this thing can be easily usable as you use Hadoop. Hopefully, you don't have to write your MPI code to directly control each machines. And this architecture is now known as the parameter server architecture. It provides you a simple program interface which are no different from a single machine memory, even though it is a distributed shared memory. And in practice, people see that, in fact, this is from our experiment, we see that the communication overhead drops dramatically once you increase the amount of synchrony bound that you can allow. Does this algorithm converge? In fact, empirically, we see that it is converging, in fact, even faster and better across different algorithms. And theoretically, we can also analyze this behavior, and we were able to prove that the quality of the divergence, of the discrepancy, and also the rate of reducing to zero, both depend on the mean and the variance of the asynchrony or of the latency across different machines. And as a result, you can actually even tune the system to your needs to control, for example, these particular two numbers to get a faster convergence. The same idea also works on model parallel algorithm. For the interest of time, I should skip that. But we have a similar proof showing you that it doesn't affect the quality of the consistency. Then I want to spend the last part of the talk on some even more advanced but slightly more specialized issues. So there is this very strange question we recently ran into on what to communicate. This is a very strange question. Well, we are doing parallel computing on machine learning model training, and we are supposed to communicate the intermediate results of the model training, maybe the updates and everything. That's almost like there's no question to ask there, right? You have to communicate that. And in fact, many of these models to be communicated are in the form of a matrix of numbers, right? So you can call this the matrix parameterized model. This is actually a pretty big family of models. For example, deep neural network models is a matrix. You can even say regression model is a one-dimensional matrix, although it is a vector. But in real case, these kind of matrices are often very big, across different models. Say here is a model for multitask regression, and for distance metric learning, topic model, neural network, we very often run into a problem which can give you a 500 million or maybe a few 100 million number of parameters. Imagine communicating this thing across the Ethernet in a cluster. Right? This is horrible because it will choke your network almost in a second. Therefore, the full update is often not practiced in a distributed environment, just because it is too expensive, to even transmit the intermediate updates across the system. So that actually caused us to think about whether this is really the only thing we can do in terms of distributed communication. Well, it turns out that the form of this update delta W often has a low rank structure, especially when you are squeezing down the number of datas used to compute this. For example, if you are computing this delta W using one data point, you can imagine the rank should be 1, shouldn't be more than 1, right? Because that's where the data source comes from. In fact, you can always establish that the delta can be expressed in the form of an outer product of two vectors. One is data dependent, the other is probably parameter dependent. And then it is the assemblage from these two pre-updates that leads to this very heavy-duty full update of a matrix. What if we focus on communicating the pre-updates instead of the updates? That potentially gives you a lighter communication overhead. Right? So this is the idea called sufficient vectors, which we explored in the past few months, and I'm going to talk about a little bit about the results. There are some difficulties in establishing equivalence between these two, because for the full updates, it is very naturally following the natural computational architecture, which is like a master-slave architecture, because you can easily aggregate all these update matrices from different clients into here by a simple summation. Therefore, you can distribute them in a very straightforward fashion. The pre-updates actually cannot be easily aggregated, because once you aggregate all these pre-updates, you start to lose the low rankness. They stop being a outer product vectors. They become a matrix. Therefore, you are going to be running into the very expensive thing. Therefore, you have to basically transmit these pre-updates one data at a time, which is a little bit expensive. But on the other hand, nowadays, people routinely use stochastic algorithms or mini-batch algorithms in which every update is actually using a small amount of data. Therefore, you could imagine that in practice, the implementation of a stochastic gradient algorithm could benefit from this new communication protocol. So, and the good thing about this communication protocol is that it has a much smaller storage trace, because you don't have to store the matrix at all. You can just store the vector form and also maybe the size of the batch of that. And this storage is also elastic. You don't have to pre-allocate the whole thing. It really could be requested on needs in your local machines. There is also a communication benefit, which I'm going to mention in a second. But just to give you, a empirical evidence, we do see that across the algorithm, different models, like I think there's a distance metric learning, multitask learning, and maybe a topic model, you actually see universal kind of improvements in terms of the convergence rate. And we actually have evidence showing that the amount of communications between the full matrix and the sufficient vectors, even though you have to broadcast it in a data-dependent fashion, is much reduced. So I want to say a few words about how to do the broadcast. Right, so here I stop short of giving you the guarantee on whether what I did just now is theoretically consistent or safe. But to discuss that, we need to basically understand the last bit, which is how this message should be communicated. Remember that we are especially machine learning people are very much used to this particular architecture, which is the server worker or the master-slave architecture. From the server, Hadoop, and Spark, are all of this type of architecture, meaning that you have a centralized place to aggregate all the messages, and you have maybe unbounded number of slaves to do the partial work. And then the thing to be communicated are those work that needs to be done. For example, the full matrix of the parameter and also the full matrix of the parameter updates. By the way, these directions need to be sent, these messages need to be sent in both directions because for each worker to compute the proper updates, they need to have the latest possible version of the full parameters itself. Therefore, they have to have this message. Then in the decentralized fashion, which is actually popular in our cell phone network and other computational infrastructure, the idea is to maybe only send this delta, the pre-updates. But again, as I said, pre-updates is as big as the full updates if you don't do any reduction. Therefore, how can we actually change the idea a bit? Right? So here I have some comparison between the two architectures, which I'm going to skip. But I want to point out that sending this sufficient factor is requiring you to switch away from the master-slave architecture to the P2P architecture because, as I said, the pre-updates cannot be, aggregated, before they were communicated. So that leads us to this peer-to-peer communication, meaning that every machine has to broadcast its pre-updates, which are the two low-dimensional vectors, into all the other machines, so that the post-updates can be computed on each machine locally from this low-rank, pre-updates. And that probably will cause you to worry some because, that means I need to have a n square or no p square number of messages in the whole network because, it is a broadcast scheme. And if my network is very big, then that's going to have you another factor, quadratic factor of the complexity. Well, in theory, that's the case. But it turns out that we have some tricks to reduce this particular protocol again, from a quadratic complexity to linear complexity in terms of the size of the network. One of these ideas is called the partial broadcast. So imagine that this is a machine learning algorithm which is not to pass the message only one time to the rest of the network. Iteratively, it will basically keep sending to the neighbors. And you imagine that even if I broadcast my message to 2 neighbors, in the next iteration, that message will be relayed to the next neighbors in our next iteration. So somehow there is this effect of information relay in the network, even if you just broadcast your message partially to a subset of neighbors. So this idea can be formalized and can be analyzed. But the effect is that you are going to generate a computational communication complexity which is only linear to the size of the network, and with a constant which is roughly giving you the size of the neighborhood you have to broadcast, which can be very small. And secondly, you can also select the volume of the message by doing the so-called sufficient factor selection. You don't have to transmit all the sufficient factors. In fact, after you compute all these pre-updates, empirically, especially in large data setting, many of the updates are redundant. You can pre-screen those redundancy using some formula, and then take out only those sufficient factors which are less redundant and send them out. So by these 2 folds of tricks, you actually could dramatically reduce also the communication overhead, the number and the size, the number of messages basically, in the network. So previously I talked about the size of the message, and now it is the number of the messages. And when you put these 2 ideas together, you are going to enjoy this. Again, across different algorithms, distance metric learning, multitask regression, and topic model, you are going to see, a pretty strong, improvement in terms of the speed of convergence, across different. In here we compared quite a few different. By the way, this is not a topic. It is a deep neural network, and implemented using popular alternatives versus ours. And you can see, the improvement is seen across different models. And also, this idea is scaling very well to the size of the cluster. When you add more and more machines, you're likely to see, a close to linear increase of the power or of the ability in handling larger problems. And with the assumption of sufficient factor broadcast, and under both, a full communication broadcast and a partial broadcast, we can establish the consistency results, which I'm not going to spell out in detail. But the take-home message is that you are going to converge to the solution, which is no different from sending out the full update matrix to every neighbor in a distributed network. So that's again, another advantage, in exploring system and algorithmic code design to get a faster solution across different type of algorithms. And this idea actually could also coexist with some other ideas. So for example, I talked first about the prompt server idea, which is a centralized communication protocol. I also talked about the sufficient factor broadcast, which is a peer-to-peer decentralized protocol. These two things doesn't have to be excluding each other. In fact, they could coexist and then communicate the amount of model parameters dependent on the needs and also the circumstances. For example, in a typical, well, I want to claim that I'm not a fan of deep neural network per se, but this is a thing that has been used in many companies. So we, as a researcher, have to at least address the engineering problems, how to get them fast. Right? So here we observe the following interesting behavior. If you look at this whole deep neural network, multiple layers, the size of the parameters actually is not uniform. Right? In the, I think in the later part, I think this is the early part of the network, you have very high dimensional matrix because you are defining low-level features, at the pixel level. Right? But in the higher level network part, you are going to work with high-level features which are much more lower dimensional. Therefore, the number of parameters to be communicated appear to be less. Therefore, these two type of parameters could enjoy maybe two different communication protocol. This one may benefit from a sufficient factor broadcast, and that part could benefit from a prompt server centralized communication. And that's actually what we did. And after you do this, you are going to see now a huge improvement, again, over the scalability of deep neural network models that is popular out there. For example, here we have deep neural network models implemented in Caffe, in TensorFlow. I think the name of the network is called the VGG18 or something. I think it's one of the winners of the ImageNet competition, which makes them very popular. The thing I want to say here is that we didn't implement this model. These models are implemented by others using TensorFlow and using Caffe. We basically just provide a new low-level communication layer for their messages to be communicated across machines. Right? So originally it was a single machine implementation, and now we have a distributed implementation. They also have their own distributed implementation, which in our opinion is very lousy, and we compare. You can see that this is the performance of different implementations across more and more number of machines. And you can see that in a terrible scenario in this particular case, the TensorFlow model starts to go worse when you add more machines, which is not actually surprising because if you have a too big a model and you add more machines and force them to communicate across machines, they choke the network and make convergence even worse. You will see some other graphs later where the TensorFlow distributed version does improve, but not as much as what we did in here. So here again, I want to make sure that all these curves are measured over convergence time, not over the throughput, which in my opinion is a more accurate and meaningful measurement of the quality of computing. So here I give you just a few more comparisons. Now it is not just one deep neural network as you see in the previous slides. We have a few other deep neural networks which are basically ImageNet winners over the past several years. And they range in terms of the architect and also in terms of the number of parameters. There are some smaller models which has roughly, let's say, 60 million parameters, which are not too big. And therefore, when you add more machines, the network is still able to handle the communication. Therefore, you see these improvements with more and more resources, even using the native TensorFlow distributed version. But when you have a larger model, which has like 100 or 200 million parameters, okay, the whole thing starts to go down, and then you can see this terrible degradation of the distributed results. But instead, in our protocol where the SVB and also the prompt server are all brought to bear to reduce the communication, we do see still a linear upgrades of the performance of the convergence rate. This is a similar solution for a different implementation of the same network in cafe, and still, I think we do quite well, using the protocols I just mentioned. So that brings to the end of my talk. I just want to share with you our experiences in jointly considering algorithmic innovation and also system communication, and hopefully do this iteratively to enable a co-designed solution. And these are the points I visited in the talk, but I think there are more questions than answers nowadays, in the scalable and universally mountable machine learning programs on different architectures. So I do want to bring attention to the especially the theory community to look into these type of problems, which does always have this part. Basically, you are going to have an ideal hardware infrastructure system, which factors into the very performance of the computing, and how to analyze that and how to mitigate their negative effects is, I think, to be a very interesting problem. Okay. So again, I didn't really touch all the issues. There are many other issues I don't have time to cover, but if you are interested, I'd be very happy to take them offline to discuss more. At the end, the goal of the project happening at CMU and also at my startup is really to turn this very intimidating picture of generating machine learning and AI solutions into something that is more standardized and more encapsulated, so that you can really intimately and carefully consider many different system, algorithmic, and infrastructure choices. But of course, when you are done with this, you hopefully can offer better performance in all these different technical dimensions. But to the users, I have to emphasize that many of the users like to see machine learning like this. They really don't want to mess up with the inner details of the system, not even programming their own algorithm. They may just want to deploy their solutions on top of their hardware, and then letting the middle layer to be taken care of by some providers. And that's, I think, what our research is trying to lead toward. Okay, that's the end of my talk. Thank you.